So we're talking about the Langlands article. And at the end of the article, there are 4 consequences that he discusses, one after the other. We've talked about 2 of them. If you don't mind, I'm just going to very briefly summarize what those first 2 were because of their great importance. And then there are 2 more, which I want to say something about as well. So these are consequences of functoriality in Langlands article. So just, I think I mixed, or I chose inappropriate notation for discussing at least one of them last time, but I'm going to just rephrase, I'm just going to phrase what I said last time using the same notation. And so the first one is, which we called 1F, first example or consequence of functoriality. And that is that any automorphic L function, LS, we're still treating only the unramified part of an L function. That's what the capital S is, meaning we've forgotten a finite set or we've left out a finite set of valuations. But LS pi prime rho prime, this would be for any group G prime, equals a standard. Godemont, Jacquet. L function, L upper S, little s, pi r, and this is the notation that I had last time, in which r was the standard representation of the group GLN for which this automorphic image from functoriality lies. And so it's the Jacquet-Godemont L functions are then you usually leave out the r because it's just the standard representation. So any automorphic L function for any group G prime equals a standard Godemont-Jacquet L function. Okay, so this is for G equals GL n. In the notation, so there's the notation above meaning what was on the blackboard 2 days ago, and hence has analytic continuation and functional equation. So I want to, after I've talked about these 4 consequences of functoriality that Langlands alludes to in his article, we're going to go back and we're going to look just in a little bit more detail about his questions, the 7 questions that he posed, because they, especially the last 2, contain the roots or the origins of what the representations, automorphic representations pi are at the ramified places. In fact, they contain more than that. They contain, it wasn't really spelled out in Langlands' article, but they contain what later became called the local Langlands classification of representations. So we're going to do that later. But first of all, I'm going to talk about these 4 consequences, the first 2 of which we mentioned last time, and this is the first one. But I'm going to say something. Yes, Waleed? That's right. So in this example, this is what I said, perhaps in a way that wasn't all that clear. But in this example, G prime is, I don't want to use G. G is, I don't want to use G, but G prime is an arbitrary group, an arbitrary quasi-split group. Phi prime is an arbitrary automorphic representation of G prime. And rho prime is an L homomorphism from the L group of G prime to the L group of G equals GLN. Okay, and so so this is an arbitrary automorphic L function. That's what that's intended to. I'd use G rather than G prime, but then functoriality goes from G prime to G, so I have a conflict, a little bit of a conflict of notation there. This is meant to be an arbitrary automorphic L function. Rho prime is what I wrote as R prime sometimes, a representation of the L group of G prime. All right, so I want to say, controversial, I don't know, but speculation, it's worth speculating. These L functions that Langlands defined are thought to include all L functions, at least all L functions that have arithmetic or algebraic geometric origins. Okay, they are thought to have analytic continuation and functional equation. That is in fact a consequence of functoriality, and we believe functoriality. But they are also thought, even though they contain some pretty peculiar automorphic representations, I think most people, if you push them, would say they also satisfy the Riemann hypothesis. So all of these L functions, let's, for the sake of argument, say that they satisfy the Riemann hypothesis, as well as analytic continuation and functional equation. It's suggestive that the Riemann hypothesis for the Riemann zeta function probably doesn't stand on it. The proof does not stand on its own. It probably has to involve some kind of induction argument that entails many automorphic L functions. I mean, if these things satisfy the Riemann hypothesis, they got to be a part of the story. And what is the story? Well, it's very suggestive, at least to me, to think that they all are part of the same story. That is, I'd have to review it to be able to say it more explicitly, but that's what happens for Deligne's proof of the Riemann hypothesis for function fields. It's an induction argument that uses many different L functions at the same time. Well, if these L functions are part of the will be part of the eventual proof of the Riemann hypothesis that in fact might be required even if you just are only interested in the Riemann zeta function, then how striking is it that we don't even know their analytic continuation and functional equation. Their analytic continuation and functional equation involves one of the deepest questions in mathematics, functoriality. So to me, those facts taken together are very suggestive. Okay, so that's so you're welcome to think about it and form your own opinions of the matter. But that's I guess that's my opinion. Until proven otherwise, I like to believe that These will all ultimately all have to be treated together. All right. Okay, the second consequence was any Artin-L function L upper S, little s rho equals L upper S. This is L upper S R. So so this, I'm using slightly different notation here, but this is for any representation, an Artin-L function, then the data that gives you an Artin-L function is any representation R equals rho, and I'm writing rho and R for the same thing in this. That's what I did before. I'm also not, just to be a little bit more concrete, I'm also not taking the base field to be an arbitrary number field, but rather just the rational numbers. Okay, so any representation, so this is a finite dimensional representation, of course, R of the Galois group. This is what goes into the Artin-L function. So this is an n-dimensional representation, homomorphism of the Galois group into GLNC. Okay, so just to make sure that we're clear, this is just to make sure we're clear on the notation, equals a standard. Godemont, Jacquet, L function, L upper S, S pi, R, where rho is identified. Okay, so rho is a representation of this Galois group, but just to be clear, putting it into the form in which we described functoriality, rho is identified with the L homomorphism. Let's say rho prime, and I'm going to write it as rho prime. This time G prime is not an arbitrary group. It's the group, as we said last time, it's the group consisting of one element alone. So it's the L homomorphism from the group GL prime, which is one direct product of the Galois group of E over Q. If you took the group G prime to be the trivial group consisting of one element, but you formed its L group, you would have to, by our conventions, have the dual group, which is just one, but you would also have to have a Galois group tagging along with it, in which E could be any Galois extension of Q. And so rho is identified with the L homomorphism. So this is not the same as my notation up there. Rho is just this representation, and I'm saying you can identify it with the L homomorphism from this particular L group into GL, which is GL and C cross the Galois group of E over Q. Okay, so this is for the group. G prime equals 1, And the automorphic representation pi prime, consisting of 1 of G prime and pi. Okay, so we've got a pi here. Okay, pi is the automorphic representation of G equals GLN, associated to rho prime and pi prime. That's when we describe the assertion of functoriality. It was attached to two groups, G prime and G, and an automorphic representation pi prime of the first group, G prime, and an L homomorphism, rho prime, from the L group of G prime to the L group of G. Okay, so it's the automorphic representation associated to rho prime and pi prime by functoriality. And this follows in the earlier notation. Okay, so this is all a parenthetical remark. There's the end of the parenthetical remark. And hence, because the Artin L function is identified by functoriality to a standard Godemont-Jacquet L function, it has good analytic behavior. In the sense that you can control its poles. And in fact, except for very few exceptions, it's an entire function. So that's what functoriality says for Artin L functions. And just to rephrase it, moreover, so this is what we talked about last time, but moreover, by associating by associating an automorphic representation pi of GLN, that's to be regarded as an analytic object. Automorphic representations are the spectral theory of the decomposition of L2 of GA over GQ. That's as analytic as one can get. So it is an analytic object, an automorphic representation pi of GLN to any Galois representation. This would be R equals rho. We're identifying R and rho up here. So this is a Galois representation for any Galois group. Let's say finite Galois group. So any Galois representation R equals rho, and so this is an arithmetic object, if ever there was one. This is an analytic object. Pi, that's an analytic object. This is an arithmetic object. We get Nonabelian class field theory, or I could say it simply the Nonabelian analog of class field theory. when mathematicians talk about class field theory, even these days, they mean abelian class field theory. And just to emphasize it, this correspondence from R, a Galois representation, to pi, an automorphic representation, is exactly what happens in abelian class field theory. This is often called, in abelian class field theory, this is often called the Artin reciprocity law. I'm going to review it a little bit later because it is the natural foundation for the Weil group, the Weil groups, which Weil introduced with abelian class field theory very much in his mind. They're a slight generalization of what happens there, but they are the subject of Langlands Questions 6 and 7, which, as I mentioned, is the foundation, became the foundation of his local classification. Okay, so my statement here is this is exactly what happens in abelian class field theory. So abelian class field theory is the special case of all of this in which G equals GL1, but it's still a formidable subject, well over 100 years old now, when you think of the special case of the ground field of rational numbers, but it is more formidable. So it's where G is equal to GL1, and Q is generalized to any number field. The base field, so Q is the base field. F. When abelian class field theory is specialized to the base field Q, it's called the Kronecker-Weber theorem, which is already interesting, but it's considerably deeper if you do it for an arbitrary number field. Okay, so this is to be reviewed presently. Maybe I won't get to it just yet, but to be reviewed soon. Just to be clear, abelian class field theory, if you take the base field Q, then that's really going to be, if you're talking about all abelian extensions of Q, that's going to be a very special case of what happens if you take an arbitrary number field as your base point. All abelian extensions of a given number field, well, that's a lot more than just all abelian extensions of Q. So, I mean, in a certain sense, Q gives much more in the case of non-abelian class field theory, because you're talking about any field extension of Q, not just an abelian one. And so you still want to know how this, how non-abelian class field theory goes for an arbitrary base field, but we are asking for much of the story by just working with the ground field of Q. That's in contrast to what happens for abelian class field theory. Question? Yes. Well, pardon me? Yes, I just did it for simplicity over Q. That's correct. Yes, yes. Just my notation was Baroque enough already for Q, so I didn't want to confuse it. But it's exactly the same assertion. Yeah.
You call it a very analytic object because of the existence of this hard measure which is needed to define this automorphic representation.
Oh, it's much more analytic than that. You're talking about it's basically Fourier analysis in a much greater generality. There's no way we would consider Fourier transforms and Fourier series as anything but an analytic theory. And this is like Fourier series and Fourier analysis in a much more general situation. It is the spectral decomposition of L2 of GA over GQ. That's analytic. It's the spectrum of a whole bunch. I mean, in the sense of spectral theory, it's even the spectral theorem, for that matter. It's a decomposition of an L2 space into irreducible constituents.
Jumping ahead. When we take L2 of you obviously have you have a representation, therefore you have operator.
A huge representation, a very reducible GA acting by left translation.
So now do the irreducible representations in that
Yes?
have meaning?
Absolutely. They have.
They should be.
Yeah, they have huge meaning. Yes.
In the subject, I assume.
In the subject. And where do they get their meaning from? Where do they get their? It might have been in relation to a question. Maybe what's your name? Max. Oh yes. I'm sorry. I think you asked at the end. You know, what's inside an automorphic representation?
That's a different. Okay.
What's inside? What makes automorphic representations interesting? What's inside an automorphic representation? It is just an abstract thing? No, it is not. I guess there's many things inside it, but first and foremost would be the local components of it. And in particular, these very concrete objects, these diagonal elements, CP in GLNC. What could be more I mean, even though this is an analytic theory, if you've got an automorphic representation, it's an irreducible representation of GA. And what does it come with? It comes with all of its local components. And at their unramified places, which occur almost everywhere, these local components are very concrete. They come with diagonal numbers, CP1, so up to CPN, diagonal complex numbers.
The things that came from chi, u, height of u, and stuff like that.
They came in two ways. I'm not sure.
Those are heights of p or
They came in two equivalent ways. They came as by construction of irreducible induced representations from the Borel, unramified induced representations, and they also came as eigenvalues of certain algebras of operators, abelian algebras of operators, the Hecke algebras. And I didn't prove why one was the same as the other, but they come in these two different, they arise in these two different ways. Yeah, anything else? Okay, so these are just two of the four consequences. I'm going to describe these consequences, but I'm not in a position to, I need to spend, I need to review for myself what Langlands did in them. The other, but I will introduce them today, and the next time I will, on Wednesday, I will describe the argument that Langlands went through to exhibit the properties, what functoriality says about these other two consequences. So other two. Okay, the other two consequences of functoriality in Langlands article. Okay, so so I just I keep referring to it, but I just recall that it's in Springer Lecture Notes 170, 1970, page 18 to 61. Okay, and they're as follows. Okay, so we've got these four consequences of functoriality. I'm labeling them 1 to 4, but with a subscript F, standing for functoriality. So the third one is the generalized Ramanujan conjecture. Okay, so the generalized Ramanujan conjecture for cuspidal automorphic representations pi of GLN. So I guess many of you know what a cuspidal automorphic representation is. I won't define it here, but the cuspidal automorphic representations, the main property that they have is that they occur in the discrete spectrum. They're ones that occur discretely. There are some other ones that actually occur discretely as well, and they were classified by Meuglan and Waltzberger, I think following a conjecture that maybe was never written down, but by Jacquet, or maybe Jacquet and Shalaika. So there are some other sort of residual, well, they come from residues of Eisenstein series, actually. They're very interesting. But cuspidal automorphic representations are the big ones that occur in the discrete spectrum of L2 of GA over GQ. You have to be quite careful if you're not considering cuspidal automorphic representations of GLN. Okay, so Ramanujan conjecture. The original Ramanujan conjecture I am not sort of too much up in the history of Ramanujan's ideas. I guess he filled many notebooks with ideas and calculations and conjectures, but perhaps this is a conjecture that has received the most attention. So the original Ramanujan conjecture is of Ramanujan applies to modular forms, in particular one modular form. The most famous modular form, perhaps. Delta Z. Okay, modular form is a function on the upper half plane that transforms in a certain way under left translation by the group SL2Z, or maybe a congruent subgroup of SL2Z. So the modular form delta Z of weight 12 So that's a full, it's a modular form for the full modular group SL2Z. And on the upper half plane, okay, so modular forms on the upper half plane have Fourier expansions. So on the upper half plane, with Fourier expansion, these are actual Fourier series relative to left translation by not the full modular group, but the group of upper triangular, the subgroup of the modular group of upper triangular matrices. And so it has a Fourier expansion delta of Z, the sum over positive integers of coefficients, tau of n, and e to the 2 pi I z. Okay. So this was a big part of people, mathematicians who studied. Pardon me? I'm sorry. Yes, 2 pi I n z. Thanks. So this was a big part of. This was sort of the most solid thing that modular forms people studied. And Ramanujan's conjecture was that it satisfied an inequality. And it's a conjecture, just a conjecture. And it was the tau of p. These are coefficients that come into the Fourier expansion. And the most basic pieces of them are the ones attached to n, a prime number. And the conjecture was that for any prime p, they satisfied an inequality that their absolute value was less than or equal to 2p to the 11 over 2. Well, 11 is supposed to be related to 12 and comes about from the weight of it. But Ramanujan, this is, people were able to get inequalities that were weaker than this, but were still very interesting. But his conjecture was the strongest of these. And it was actually, I guess, stayed open, an open question until Deligne established it in the early 1970s. Yes.
Possible to give some motivation for how originally they were, so why they originally became interested in the delta function, and also why they realized that this kind of inequality had significance.
The delta function is interesting because you can correct me if I'm wrong, I'm not really an expert on these things, but the delta function is a modular form, and I think it's the first one that arises with the full modular group as opposed to some congruent subgroup. If you take smaller and smaller congruent subgroups, you are then asking for a modular form with a lot more information in it, because it's only invariant under something smaller, or only equivariant with respect to something smaller. So the smaller and smaller you make the congruent subgroup, as say congruent to 1 mod n for a large n, the more information and the more difficult is the study of the modular form. But this is, I think, the first one that's modular. Is that right? Is that a
smallest weight cusp form for SL2.
Okay, smallest weight cusp form for SL2Z. So, and it's a multiplicity 1, so it's very nice, I guess, for the study. Yeah, Mellars. Mm-hmm. Uh-huh. That's very nice. I guess I sort of have heard that, but I would like to maybe take some time off to study these things. I in fact, have had a book by Sayre, I don't know if it contains this, out of the library for several years. They haven't they haven't really come after me too much, but I need to take it back. But he studies all kinds of inequalities and equalities of the form of the kind that you mentioned, actually. And it does seem very interesting.
So now the functions related to these variables. Yeah, because okay. You can say that partition function, but you want to know how they are distributed and the congruence that they satisfy. And it is considered the reason I'm asking is I do understand that the direction to representation. So Ramanujan synthesis by me. I don't know, Ramanujan was super interested in partition there. He wanted to discover a partition function. So now we could get it to the two versions of this. Well, this thing appears as part of the generating function. Generating. Q times product of 1 minus Q. And so, and so it gives very that's the problem. And so it's how it's related to the non-determinant. Sorry, we're taking.
No, that's fine. That's fine. No, that's fine. In the context, in the context here, the fact that that it's a congruence, that it's a modular form for the full congruent subgroup, means that delta of z. Well, delta of z. We've said that modular forms correspond to automorphic representations, and what this corresponds to is an automorphic representation I of GL2. So I've mentioned that there are two steps that will get you from a classical modular form to first a representation that occurs in L2 of GR modulo, and that's invariant under a congruent subgroup gamma, and then that's the first step, and then the second step is to think of it as something that corresponds to an irreducible representation of GA that occurs in L2 of GA over GQ. So this corresponds to an automorphic representation of pi of GL2, and the fact that it is attached to the full modular group means that it is unramified for all p. So in the notation that we've been talking about, this means that the exceptional set of valuations where it is ramified is very small. In our notation, it corresponds only to the one Archimedean valuation of the rationals. Okay, so that's the way it. I don't know when he posed his conjecture. I guess I don't even know if these things are dated, but I guess he must have done it with Hardy, or when he was with Hardy and in Cambridge, and left many notebooks with such things, including much calculation. But sort of well after that, I think it's Sataki, and so this might have been around 1960. Maybe plus a few years. Pointed out that Ramanujan's conjecture for delta is equivalent to saying that the automorphic representation pi, this is the automorphic representation pi attached to delta, well, it turns out that the strongest of inequalities says precisely when Satake unraveled it and looked at what it said for the automorphic representation, it is tempered. And what this means, Harish Chandra actually has described what tempered representations mean for any real or p-adic group, for any group. But in this case, for GL2, what it means is that if pi p goes to CP, remember, if it's unramified, which it is for all primes, this is for P prime, and if that equals C1 and C2, which is what we've agreed happens when you have a prime that's unramified, you get for GLN, you get a diagonal matrix of complex numbers, and CK equals CK of pi p is in C. Then to say it's tempered means that CK, it's a complex number, non-zero complex number, so I'm sorry, this is in C star, then this means that CK equals 1 for every K. In other words, CK, any one of these numbers, equals I guess I'm talking about just GL2 in this case. So CK equals e to the 2 pi I theta k, where 0 is less than or equal to theta k, less than or equal to 1, and k is one of these two diagonal entries. And it corresponds, each of these CKs then corresponds to, it doesn't just correspond to a character from the p-adic field to, which is what we would be talking about in terms of the parametrization of these things. It corresponds not just to a complex valued character, but not just to a non-unitary character, but a unitary character. So it corresponds to a one-dimensional, understood, a one-dimensional character of GL1 QP given by well, given by this number. So it's given by the character that sends XP. in QP star to CP, which is evaluation of XP equals CP to the minus log P of XP to the P. CK being this e to this imaginary complex number. Okay, so at the very end of his article, so that's what tempered means for representation of GL2, automorphic representation of GL2, or GLN. The representations in the discrete spectrum that come from residues that were defined by Mögelen and Waltzberger don't satisfy their characters. The CKs are characters, but they're not of this form. They're real. They can be real characters. The trivial one-dimensional representation of GL2, for example, is it occurs in the discrete spectrum. You can have the constant function, if you mod out by the center of GL2, say, or take SL2, the constant function on GA occurs in the discrete spectrum. It corresponds to the irreducible representation of the group that's just constant. Well, because GA over GQ, when you mod out by the center, because it has finite volume, the constant function occurs in the discrete spectrum. So that is not a cusp form. It's something exceptional, and its parameters do not satisfy this property. They have they're basically real exponents. So it was not Sataki said, Ramanujan's conjecture says that this automorphic representation of GL2 is tempered, and there's lots of it's unitary. The automorphic representation is certainly unitary, but unlike the case of abelian harmonic analysis, unitary when you're talking about representations of a real or p-adic group does not imply that they are cuspidal. And so Langlands used functoriality. He assumed functoriality, and in a one-page argument, right at the end of his article, he uses it to prove Ramanujan's conjecture, or really its analog for general linear groups. So I have to go over that, and I'll present it next time. Yes. Yes, CK, I haven't always put in the notation. This is CKP. So that's theta K of P. It depends on P. Each of these things depends on P. And the fourth, I'll just say that the fourth question is if we agree, if Ramanujan's conjecture has been solved, so each of these characters lie, say, in the unitary group on one variable. In other words, they lie on the unit circle. The fourth question, which Langlands devotes one sentence to, and says he doesn't know the answer. But if once you know that they're all tempered, and so that these different, as p varies, these parameters all lie on the unit circle, how are they distributed on the unit circle? And that's a very famous conjecture. Just for GL2, just for SL2, a very famous conjecture known as the Sato-Tate conjecture, which was proved more recently by Richard Taylor and Closell and others. So Langlands devotes one sentence to it. Says he doesn't know what the answer is. I guess the Sato-Tate conjecture just applies to GL2, just SL2. Langlands talked about these distributions in general, but he said he didn't know what the answer was. And indeed, it's still extremely deep and interesting, even to just formulate what it says for other groups. Question? So I'll spend one more, well, part of one more day talking about these things. Then I'm going to go back and systematically just review. I've talked about what functoriality is, but it's actually very worthwhile to just say what the 7 questions were. In order, I'm most interested in the last 2 questions that evolved over the years into the local classification of representations of any group. So I want to do that starting maybe next time.